One more example is the magnetic field of a circular loop. So magnetic field formed at the point on the x-axis. The loop is located on the yz planes. Circular loop is flowing from here and making a circular loop on the yz planes and flowing parallel to the z directions. Then we would like to find out the magnetic field formed on the x-axis here. This is the field point. Distance between the origin to the x-axis, this is x. The magnitude of the magnetic field formed by this dl can be calculated. Mu sub 0 I over 4 pi times the dl over x square plus a squares. And the distance between the line segment of the dl to the field point, this r is expressed using Pythagoras theorems, a square plus x squared and square root. And r square becomes x square plus a squares. So this is the magnitude of the dB. And then we'd like to find out the component, x component of the dB, dBx, and the y component, dBy. So to find out the x component, you need to multiply the cosine phi. So cosine phi, if you consider this triangle, cosine phi can be calculated very easily. It's a over square root x square plus a squares. And the sine phi is x over square root x square plus a squares. And if you multiply the dB cosine phi, it becomes a dB sub x. So dB sub x is a dB cosine phi. dB sub y is a dB sine phi. So we have an expression for the dB sub x, dB sub y. A component of the magnetic field formed by the circular loops, total magnetic field, can be calculated using the integrals. If you integrate of the dl of the circular loop with the radius of the a, circumference of the loop is a 2 pi a. You can find that the mu sub 0 I over 2 times a square over x square plus a square. The power index is a 3 over 2. In the case of the y component, if you consider this line segment, positive d sub y is given. If you consider the line segment, this line segment expressed by the green one, magnetic field formed at this field point should be directed downward. So y component is opposite directions, b sub y. So y component should be cancelled out with these two. Then we expect y component of the magnetic field becomes 0. So if you consider the circular loop, magnetic field formed by the circular loop is directed passing through the center of the circular loop and directed in this direction. So again, we can apply the right hand rules. Right hand rule is used to find the direction of the magnetic field. You can follow the directions of the current using the fingers, following the current direction of the current. Then some point the directions of the magnetic field. Okay, this is the right hand rule. B sub x, I expressed B sub x can be expressed 1 over 2 mu sub 0 IA square over x square plus a squared 3 over 2. And IA squares is a magnetic dipole moment. This is the magnetic dipole moment. So it becomes 1 over 2 mu sub 0 mu over x square plus a squared 3 over 2. If you consider the x is much larger than the radius of the circles, it becomes nearly equal to 1 over 2 mu sub 0 mu over x cubed. So if you consider the permanent magnetic field is about 1 Tesla. If you consider at the x equal 1 centimeters. So this is about 0.01 meters. We would like to find out the magnetic dipole moment of the permanent magnet. Can be calculated 2b sub x cubed over mu sub 0. And then you can substitute b is 1 Tesla, x is 0.01 meters, and mu sub 0. It becomes 2 times 1 Tesla, 10 to minus 2 meter cube over 4 pi times 10 to minus 7 Tesla meter over amperes. It becomes 1.6 ampere meter squares. So it's about 2 ampere meter squares. This is the magnetic dipole moment of a permanent magnet we could calculate using the today's lecture contents. How can we create this magnetic moment? We could consider the atoms. If you consider the atoms, at the centers, nucleus has a positive charge, and the electron has a negative charge is circulating around the nucleus. So if you consider circular motion of the electrons, current can be calculated electric charge divided by the period of the circular motion of the electrons. So Vt should be equal to the circumference of the 2 pi r. So T can be expressed. So current due to the electron can be calculated is EV over 2 pi r. So magnetic moment is calculated I times A. So you can substitute this I. And A is the areas of the circular orbit. This is a pi r squares. Then substitute. A is a pi r squares. It becomes 1 over 2 EVR. And the angular momentum of the electrons is calculated MVR. So using these two equations, you can express the magnetic dipole moment. Use the angular momentum. E over 2m times L. And if you use the knowledge of the quantum physics, angular momentum is expressed the integer multiple of the h over 2 pi. So substitute this L into these equations. You can find that the magnetic dipole moment of a single atoms can be expressed is this expression. Mu equal E over 2m times h over 2 pi. So we call that this is a Bohr magnetons. The magnitude of the Bohr magneton is about 10 to minus 23. So it's about 10 to minus 23. Then if you consider the 1 mole atoms, you have to multiply it. 6 times 10 to 23 times Bohr magnetons, mu sub b. If you substitute these quantities here, it's about 5 ampere meter squares. So in the last slide, we derived the permanent magnet has a magnitude of the dipole moment of the 2 ampere square meters. If you consider the 1 mole atoms, 5 ampere square meters, we have a comparable value of the magnetic moment. Okay, this is the end of this session.